Okay. Okay, let me check. Everything is fine. Okay. Maybe I should start. Um, Hello, everyone. Hello from Alicante, Spain. Um, I'm really excited to be part of this awesome event because it's quite difficult to find embedded conferences delivering such amount of excellent content. I would like to thank Marcus Tucker, maybe it's over here, for pointing me out to the existence of this emBO ecosystem I was not aware of. Thanks a lot to the organization, to the sponsors, and the rest of the speakers, and also for you, all of you, for making it possible. Uh, Let me check if I can manage my slides. A little bit introduction about myself. Well, I'm a telecommunication engineer with major in electronics. I have been in the trenches from the last 17 years, developing hardware and software, both for embedded and embedded products. But more important than where I've worked or what I have made and when, is how I made it. During the majority of those years, I barely managed to survive. I consistently failed to follow a sustainable, iterative, defect-free development process in every project I was involved. And I was not alone. Every team member I met had the same shared belief that the embedded was that hard. Things drastically changed when I discovered, guided by pain and nearly by accident, this awesome book from the master James Greening, which it was TDD 7 years ago when I found that book, which pointed me out to the extreme programming, agile, and craftsmanship. For an engineer that had been living what is called the software factory, it supposed a whole game changer. Somehow I felt like I had been living inside a Plato's cave. Present Talk tries to synthesize which are the major impediments I have found as a part of the factory's cave's underlying culture, the path I have followed to abandon those landscapes made of waterfall interconnected silos, and some of the solutions I use to eliminate or reduce those roadblocks. I am going to talk about some technical practices, but also, and more importantly, about the principles and values that sustain them. The best way to learn is by teaching and being taught. That is why I'm here today, and it's also the reason why I occasionally help teams and organizations to improve their development processes, offering both online and on-site technical courses, mentoring, and consultancy. You can find more details about me and my services on my website and LinkedIn. So let's start. Let's start by trying to define a minimum common ground. We we all will agree that an embedded system is made of hardware, firmware, and hopefully some piece of software. But what is really hardware? We all will agree that the yellow shaded area is hardware. But what about the microcontroller itself? It's a piece of silicon, isn't it? Well, from the point of view of the embedded code, the special function registers are hardware as long as each microcontroller unit has its own implementation. These registers are a simple way of having the hardware mapped into a set of memory addresses in which each single bit has a special and unique meaning. They are the gateway interface to the real world, that world that our embedded system senses and tries to actuate accordingly. And that point is extremely important for us, as long as, for the point of view of our embedded code, absolutely nothing happens in the real world if it doesn't change a special function register bit. Because while we are developing our code, trying to rule the real world environment like temperature, speed, or whatever, to indirectly generate the desired Maxwell law outcome, which will end up causing the change in the special function register bit we are currently interested in, is usually expensive and difficult to reproduce, as well as a waste of time and electrical energy. This kind of development process isn't fast enough in order to be used as our control feedback loop to iteratively, by means of baby steps, improve our products. A much better approach is to simulate the operation of the desired external event by means of another software entities called test doubles, which can be able to interact with the special function registers, setting them up the desired bit flag at our convenience. The point here, the main point, is to realize that our embedded code will respond exactly in the same manner, independently of how a hardware gateway related flag has been activated. That's the whole point. So we have clearly delimited where the embedded code ends and where the hardware begins. But That embedded code, is it firmware or software? I love the following definition from James Greening in Clean Architecture book from Robert Cecil Maltin. He states that the software is this thing that can have a long useful life, but firmware will become obsolete as hardware evolves. Or another word to say it is that firmware is firmware because of what it depends on and how hard it is to change those dependencies. When some dependencies are hard to change, it will be indicated by using this icon during the presentation. Another piece of gold that explains James in this book is that non-embedded developers also write firmware whenever they split libraries or platform dependencies throughout their business logic code. This is a great advice. If you are an embedded developer, be aware that the special function registers are not the only thing that you can end up being firmly tied to. Your operating system, real time, or vendor libraries are, for example, are also excellent candidates to end firmly depending on. Let's move now to the three well-known and desirable steps of software development, known as the make it work, make it right, and make it fast. During the make it work phase, we are focused in understanding how to solve the problem, not about engineering the code right. During the make it right phase, we are supposed to be engineering and crafting the code right in order to make it easy to understand, maintain, and evolve. And these two differentiated steps should or must exist because barely no human being, and therefore none of us, is able to do both things properly at once at the same time. And the last step is make it fast, which means fulfill the system requirements if there are any of them. And now I'm starting a section or opening a section in the talk that I call fallacies and mantras. And here comes the biggest lie ever. Is believing that we are able to find the right solution at our first iteration. That, and this slide shows a fully decoupled portable architecture. The trap is to think that something like that has been completely designed up front and developed in a single iteration. That kind of thing is impossible both in embedded and non-embedded environments. But in my opinion, the major difference between embedded and non-embedded environment is that making a simple thing to work is orders of magnitude harder in embedded world. And this is because we have to manage those low-level details at once in order to accomplish this simple task. Additionally, the underlying running hardware platform is usually scarce, non-existent, or even faulty. In my opinion, starting from our academic studies and continued by naively following most of the examples and application notes coming from the manufacturers themselves, and finally perpetuated by the lack of really senior developers out there, some of us, like me, have faced the situation illustrated in this slide, which is known as the main God. In this example, this is an example of how it looks like in code. It can clearly see how the single main module is in charge of everything, including interacting with the hardware. That has a direct consequence. The code is firmly tied to the specific running microcontroller unit, and additionally to the target cross-compiler. The reason for the last sentence is because most cross-compiler vendors usually offer some kind of aids in order to safely interact with a special function register. So why are not we going to naively use them, right? Moreover, the code knows exactly which integrated circuits are being used in the current solution, that is the current hardware variant or PCB assembly. So it's fully tied to use these components in order to perform its higher level duties. And the hard to change dependencies do not end here. The code is also fully aware about how the microcontroller is connected to the integrated circuits in the current PCB layout. For these reasons, we can safely affirm that this code is firmware. It's firmly tied both to the running microcontroller unit and to the underlying hardware platform. If we attend to design principles like solid, for example, we could affirm that it violates all of them. But I am quite sure, however, that many of you will have been lucky enough to haven't had to deal with the main God like I had to do, because you have used layers, specifically what we commonly know as the driver's IC layer. In this layer, we put the modules aimed to command the specific IC peripherals accordingly to their data sheets. In order to do that, the IC driver modules use the special function registers to drive or communicate with the chip. which again makes these drivers strongly dependent on the running microcontroller unit. That means that it's not possible to execute them by another microcontroller, or in other words, they are not portable. This is a clear violation of the dependency inversion principle because a higher level entity, it was supposed, the driver in this case, depends on low level details, like is the running microcontroller unit. And what about the code that uses the drivers layer? That is the application layer. Well, it knows exactly which integrated circuits are currently used, as long as it's directly calling them through their public APIs. That supposes a clear violation of dependency inversion principle. The application is supposed to be the highest level entity, but it depends on the lowest level details. And also a clear violation of open close principle because we are not open to substitute, for example, an integrated circuit for another one that extends functionality, maybe extending functionalities without having to change the application code itself. As a resume, we could say that these layers, the layers that the easy drivers layers, somehow are elusive, right? It improved a little bit the cohesivity of our code if we compare with the main code, but the underlying hardware, the underlying problems are still there. Some of the problems of main code are common to embedded and unembedded. For example, we have no long life software in charge of capturing domain or business logic. Nothing is modular or reusable. It's nearly impossible to test any part on isolation. We are forced to perform manual testing and debugging, and what it leads to an expensive and hardly repeatable process. Additionally, due to being embedded, this code compiles only with the selected cross-compiler, executes only under the specific microcontroller, and it runs only under the specific hardware platform or PCB assembly. As a result, expensive and scarce powering input generation and output measurement equipment is needed. All these problems materialize in a huge bottleneck, the hugest one for our development process that we know as the hardware bottleneck. And this is an example of how the hardware bottleneck tends to materialize in our workplaces. Hardware bottleneck presents lots of issues. When we are forced to debug our code directly in the hardware, we are exposed not only to the bugs coming from the code, but also to the errors coming from the hardware itself. If we try or test new code directly on the hardware and it doesn't work as expected, where is the problem located? Is it hardware? Is it firmware? Is it both? Well, this situation commonly leads to a lack of trust, preventing us from behaving as a real embedded team. Additionally, there are situations where it is nearly impossible to get the environment conditions needed by our test by means of trying to rule any Maxwell law. In the slide, you can see the state diagram to be followed in order to store a byte in a flash memory, as stated in its manufacturer's datasheet. In green, we have what we know as the happy path. That is the sequence of actions to follow when everything goes right. If we are implementing a driver for this flash, this path is for sure fully implemented, because if not, we won't be able to store any data on it. But the tricky part comes from the sad paths. That is when some error or exception occurs. In red, we can see 3 sad paths. How do we test in hardware the expected behavior of our product when, for example, we are experiencing a BPP error? It's very hard to do it. As I said, it's almost impossible to reproduce those situations debugging with the hardware. Again, test doubles are at our help here, specifically a kind of test double known as a stub, which allows us to provide the indirect inputs used by our production code in order to make it execute the desired code path. What I have seen happening in these situations is one of the following 2 options. The first one is when the production code does not implement the sad paths at all. It's nothing there. And the other one is that the second one is when the sad paths are implemented but not tested, untested. This problematic scenario does not only appear when we have hardware dependencies. It's also very common when a test later approach is followed, when the inadvertent accidental complexity that we have been building up, it forces it during where we are developing the production code finally shows up and forces us to surrender about trying to test these currently difficult to reach corner cases. If we let something without testing, we are opening the door to the one of the testing antipartens that is called the liar. We think that our tests are covering everything, but they aren't. So this is the one of the most important antipartens to overcome. As a result, we end up leaping, yeah, what I said, the testing antipattern, right? Um, and the aforementioned problems tend to lead to the sensation of apotheosis when we finally manage to bring up the system. Yeah, we have a word for that. We have bring up the system. We tell to ourselves it was complicated, but we finally make it work, without realizing that the vast majority of this complication wasn't essential, was but pure accidental. Which are the reasons, in my opinion, that have led us to this discouraging situation? There are several root traps. Some are common to embedded and non-embedded, and others that I think are more accused in the embedded. Let's go for the first one. This trap, in my opinion, is typical in the embedded world, and I call it the vendor's trap. What it says is that the vendor IDEs, frameworks, utilities, toolchains, libraries must be low-level details, properly hidden and decoupled from our application. Or, in other words, the vendor is not your partner, is not our partner. At the end, the running processor should be a low-level detail. Not paying attention to this trap causes a great competitiveness disadvantage due to the enormous effort needed to migrate from a running platform to another. Traditionally, most companies have dealt with this pain by means of diluting the migration throughout several years. The problem that I see is that the world has drastically changed, as for example, the semiconductor shortage has recently showed us. Even companies from traditional sectors where the projects were relatively well specified, as long as the number of uncertainties were relatively small, won't have those time margins at their disposal anymore. Another trap well spread in the embedded world is the compliance mindset trap. First, let me define the quality in four quadrants somehow. One axis represents what is visible to the client. The other axis represents the kind of value, positive or negative, both to the client and to the organization. On the right side, we have two quadrants visible to the client, which conform what is known as external quality. While providing new functionalities and features has a positive value, delivering products with defects or bugs has a negative impact. Most of us, like me, for example, interested in testing, became interested in testing in order to mitigate or the number of bugs that we were delivering to our customers or clients. In the embedded world, we have some epic and historical failures in our mind, like, for example, the 42nd flight of the Ariane 5 originated due to an overflow when converting a 64 bits floating point number to a 16-bit signal integer. Or the TDD-25 linear accelerator, which killed at least 6 patients after receiving 100 times overdoses due to race conditions in its deficient software. Or the 89 deaths originated by the unintended acceleration of some Toyota models due to an overflow problem on the real-time operating systems stack. As an attempt to mitigate these situations, safety quality standards are considered the crown jewel of preventing bugs inside the embedded world. Most of the recommendations are followed consciously or unconsciously by the vast majority of embedded developers. For 6.15.08 standard, dynamic testing is considered the primary functional validation technique. For these reasons, and accordingly to each safety integrity level, it points a clear focus on code coverage. 100% code coverage is highly recommended, which means somehow mandatory, for those systems with the highest safety integrity levels. Before going deeper, let me make a little introduction to a powerful technique that is still not required, as far as I know, in any safety standard. It's called mutation testing. It's an automated fault injection technique aimed to find counterexamples to this conjecture. Our test suite is comprehensive because it has 100% code coverage. Another way to say it is that it's aimed to automatically measure the quality of our tests. Here you can see a code example from the kata we developed during my embedding system course, a temperature controller. You can see that it reads the temperature on line 19 and it compares to a configured threshold. Depending on the situation, sends a temperature control action to send to a certain actuator. As you can see, lines 21 and 22 are not exercised by the test suite, which is known as they are not covered. The 20 mutants of these two lines pass the test, which is known as they are alive. The fact that they are alive means that our test suite is not comprehensive or semantic stable as long as these two lines could be completely removed and our test suite wouldn't notice it at all. So even when a 90% code coverage could look like a great number, it isn't. Um, Another of the fallacies that I heard related with the code coverage from time to time is that code coverage is a useless metric. And another way, sometimes it adopts other forms, like, for example, we have 100% code coverage and we are still having defects, so we can give up on that metric. And that's wrong. We can strongly affirm that any part of the code that has not been executed by the test suite is for sure out of our control. Code coverage metrics helps us to locate and identify these zones. The only valid uh, target, the only valid target for this metric, even being really difficult to reach, is 100%. Obviously, if we follow TDD, 100% code coverage is assured by default. Another way to say that is that 100% code coverage is a precondition to have a comprehensive suite of tests. It's a necessary condition, but not a sufficient one. Having this in mind, why does a functional safety standard allow any value below 100%, at least for the lower safety integrity level systems? And not only that, but also why does it open the possibility to accept code coverages below 100% if an appropriate explanation is given, even for the highest level safety critical systems? Well, the only reason I can imagine is to be somehow permissive to accommodate certain test later approaches inabilities. Let's see another example. Now we have 100% code coverage, but there are still 3 mutants alive. Mutants on line 20 and 24 are symmetric. Let's take a look at the mutant on line 20. What is this mutant whispering to us? As you can see, what it has done, it has changed this greater for the greater or equal, and our test suite is happily passing. Uh, well, what this is really saying is that we have not specified which is the expected behavior for the quality corner case. The question is to make now is this a bug? Well, it really depends on what we were expecting to do in the quality case. If we were willing the temperature actuator to do not actuate in the quality case, then that is when the ambient temperature is just in the limit, then it is a bug. We have discovered a bug. If we were willing it to actuate or it really doesn't matter, then it's not a bug and we can consider this mutant as an equivalent mutant. Let's imagine that it was a bug, right? If we add the tests corresponding to the symmetric corner cases where the ambient temperature is just at the upper and the lower limits, as we can see here, these two tests, right? We have killed those mutants. That means not only that we have improved the semantic stability or the semantic stability of our test, but also that we have effectively removed a bug. Let's take a look now to an empirical study of the application of mutation testing in a safety critical system coming from the industry. It's applied to a 60,000 lines of C code with 100% full code coverage, giving as a result more than 27,000 of alive mutants. What the hell, right? A sample of 200 alive mutants was selected to be inspected and analyzed with the engineering team. The result was that this sample revealed that at least 2 faults or bugs in the production code. If we extrapolate these numbers, considering a uniform distribution of defects, we will end up with the possibility of having 271 defects in the code that waiting to be executed, even when we have 100% code coverage. That leads me to another or the fallacies that are related with the code coverage and that I usually hear. It's like it says that the code coverage is a harmful metric. And the underlying reason behind this affirmation is that many developers try to hit 100% code coverage simply because they were somehow mandated to do it, without really understanding or even sharing the reasons and implications behind it. Being so, some of them end up cheating the code to artificially increase the code coverage. And that leads me to another section in the talk that I call the takeaways. And here comes the first one. This is not a metrics fault. Cheating the metrics is a science or bigger cultural and professional problem. If you add mutation to testing to your workflow, the cheaters, being developers or managers, will be unmasked. This is another great paper about improving the testing quality by means of mutation testing. Apart from its results, quite similar to the ones shown in the previous one, what I want to emphasize is this sentence, which I think it clearly resumes the dangers behind the compliance mindset trap. Do we really test our products in order to fulfill the required certification? Or should be this fulfillment simply a direct consequence of following our internal standards and development processes? Engineering danger alarms must always go on when we start thinking about simply fulfilling a normative without thinking about the whys behind it. As a takeaway, I will say that our internal development and quality standard must be there in order to raise our internal quality high enough to preserve our organization, enabling us to deliver value to our customers in a sustained pace. If we do this properly, fulfilling any other external quality related standards will be taken for granted. Another trap, common both in embedded and non-embedded, which has a direct implication with the previous one, is the deviated focus. As I said, most of us became interested in testing or even TDD to prevent the number of bugs we were producing. But bugs and also our inability to deliver new functionality in a sustainable pace are only the visible effects of another most important aspect that we will see in a moment. Let us take a closer look into the TDD red-green refactor steps. As I said, making a simple thing work, it's orders of magnitude harder in embedded world. If we use TDD, we will first put the self-checking specification in place in order to enter into the red phase. The rule here is to write only enough test code to demonstrate a failure. The goal of that rule is to assure that our automated cause effect relationship checker works properly. Now it's indicating that we are not fulfilling the new spec. Once there, we will be trying to bring up the new functionality. Reaching the green will mean that we have made it work. And we will try to do it as fast, as simple as possible, right? We are allowed to be a complete sinners. The goal is to reach the green as fast as possible, doing the simplest implementation. Here, we can copy from Stack Overflow, or even we can use that awesome vendor's tool that auto-generates some HALs that most of the time should be better called files from family abstraction layers instead. As you can see, there's nothing new to us here because somehow it's just what most of us have been doing so far during these years. The TDD rule is to write only enough production code to make pass the failing test. Why? The goal is to do not introduce more production code than the necessary, saving us from unnecessary accidental complication and also to the possible apparition of the uncovered side effects. Do you remember the liar anti-pattern that I mentioned before? If we follow these two stages of TDD, we could say that we are following a test-first approach, which is primarily focused on assuring external quality. But TDD has much more to say than direct external quality assurance. When we are in green, we must enter into the refactor phase. Paying attention to this phase means that we are really applying or doing TDD. In this phase, when we enter into the make it right phase of software development. It's here when we must engineer or code right. Here is where we apply software engineering principles like this simple design, solid design patterns, all the tricks that we know, right? And it's here where we take a closer look to our dependencies and try to properly manage them. The two left quadrants, which conform what we know as internal quality, even invisible to the client, are much more important because when we have a well-engineered code, then the number of defects are much more smaller, and so the bugs finally delivered to our customers. TDD, while helping us to massively improve the external quality through following its test-first approach, it's really aimed to enabling us to improve our internal quality iteratively through a series of continuous and safe refactorings. That's the aim of TDD. But yeah, how does internal quality looks like, right? For those that came from the software waterfall factory, it's really complicated to figure it out, as long as we usually do not have names or concepts to properly talk about it. We rely on our feelings and sensations. Like the more pain, the less the quality. As a side note, if you do code reviews, you should better go to pair programming or assembly programming. You could try that. It's a better approach. Um, Even on the specialized technical papers, one need to read between the lines. As we have seen that we had 270 faults, possible faults as an external indicator of the quality. But what about internal quality? As you can see, it says that the component sizes range from 200, 400 lines to 7,000 lines of code. The single responsibility principle seems to be outraged here. Um, in fact, if we refer to the AEC 61508 standard itself, we will find a section about modular approach, where it is indicated that it's highly recommended to limit the size of a software module and manage their complexity. And that is not only because of the rigidity that it supposes, but mainly because the bigger the module, the higher its cyclomatic complexity, and therefore the increased difficulty to comprehensively test it, which leads to a higher defects ratio. I have tried hard to how these two things can be matched, but my brain is not so good at this. So another fallacies that I usually hear is that we can test this, we can get the same benefits following a test later approach. And no, that's wrong. Test later are testing techniques focused on external quality only. They have nothing to say about the design or development. Another, as a takeaway, is the quality is not coffee sugar, right? Inspection does not improve the quality. The quality being bad or good is already there. That's why we are trying to shift to the left all the quality assurance. But what about the agile and string programming in safety-related environments? In the ISO 26262, which is an adaptation of the 61508 for the automotive industry, even when the reference software development process is the V model, they are finally opening to accept approaches and methods coming from the agile world. Specifically, in the first example, is saying that test-driven development can be used to improve quality and the stability of requirements, and that are great news because it means that it will unconsciously reach a larger number of embedded developers out there, more or less like it arrived to me. But what about the making it fast? We are embedded developers, and we usually have tight timing requirements, even if we are not developing a real-time application. Well, I delayed presenting this development phase consciously, as long as it's related with the very last of the trust common inside the embedded world. I call it the global performance pre-optimization trap. As Ron Jeffries states in Refactory's book of Martin Fowler, even if you know exactly what's going on in your system, measure performance. Don't speculate, because you will learn that 9 times of 10 you will be making useless optimizations regarding performance, but a negative value regarding code understandability, maintainability, reusability, and extension. So the first question should be how fast? If we do not have a clear specification, now is the moment to clarify it. Once we have an objective number, then is when we finally have the timing specification and not before. Once we have it, once we have this timing specification, what we need to do is to translate it to a self-checking spec just with the other ones going to the red. Our tests can use, for example, the microcontroller timers for this purpose. And as another requirement, what we will try to fulfill it as fast as possible. We don't have to engineer anything here. And once we are fulfilling the time specification, we are ready to move to the make it right phase. That is to the TDD's refactor phase. Now is when we will try to make the code as decoupled and clean as possible, employing all the software engineering techniques and tricks at our disposal. Like, for example, using the CRTD pattern seen on the Michael Case model C++ in embedded system talk on the emBO 2018 edition, while we keep fulfilling timing specification during all the process. Another takeaway comes from Martin Fowler. The secret of fast software is to write tunable software first and then tune it for sufficient speed. The last of the traps that I'm going to share today, maybe it's a common trap. It's not for embedded, and I think is the most important one is the knowledge and skills trap. No human being can escape to the Dunning-Kruger effect. The natural tendency is to think that we know more than we really know, at least until we become really seniors, which does not have a direct correspondence with years of experience. High humility threshold prevents us for continuous learning and continuous improvement. So we better should follow one of the most valuable advices from one of our beloved masters, Dijkstra: be a humble programmer. So what we need is to move from the making it work on the survival mode into making it right. So behaving as engineers. What we need is a new approach, an approach that is usually outside the usual embedded limits. As James Greening explains in his wonderful book, what we need is an embedded dual target TDD workflow. What we are going to do is in the stage one is to follow the red green refactor phases in a host based flow, that is in the machine or platform that we are developing. We will generate the self-checking specifications. We will fulfill the specs as fast as we can. And once we are there, we will improve the structure of our code iteratively with a cadence of maybe 1 minute or less, right? That's the flow on the host. But as long as the end machine is different from the host, we need to run all the specifications and also the whole product under the target microcontroller or target device. That is what we do in stages 2 and 3. Daniel Penning explains that really well why this is nearly mandatory in his talk, The Hidden Risk in Off-Target Testing in the past emBO edition. We will cross-compile our solution and we will execute the same tests under an evaluation hardware or demo board. If we found that loading it into the evaluation hardware supposes lengthy slots, delaying our feedback loop, we could use a microcontroller unit simulator supplied from the vendor. It is here where the vendors should provide the correct tools. A simulator should be one of these tools to be considered when we are selecting a vendor. The target-based flow is lower than the host one, so the cadence between completed suite runs could be in the order of 5 minutes. As always, the shorter, the better. So, and the main benefits of TDD or dual target TDD is that it will remove the fear, because we will be incrementally developing our solution that is going to be comprehensively tested at least on 2 different platforms. The fast feedback loop that puts in our pocket will encourage us to try new approaches and decoupling and new structures and new architectures that were nearly impossible to try before. We will learn fast, maybe failing. We will fail, but failing fast. But the objective is to learn fast, without limits, as long as new tools will be finally available, like static analysis, rule checkers, comprehensive functional and non-functional testing, mutation testing. And when I say finally, I mean that they are going to be able to be applied to a 99% of our code base. Only the 100% corresponding to the firmware thin layer maybe will be unable to be processed by some of the tools. This toolset is going to be run automatically by the continuous integration and continuous testing server anytime a code change is sent to the source control server. This is an example of the pipeline we study in my course, where we run several stages in the host, like static analysis, dynamic analysis, and we extract some metrics like code coverage, mutants coverage, and cyclomatic complexity. The same kind of dynamic analysis is done in the target when everything has gone fine in the host. Here, we also extract some cross-compiling metrics that are really interesting, like, for example, the warnings. Those warnings that some of us usually tend to forget while we must go to a clean build. This is an example of the information that is extracted and how it's represented for each build. That situates us in an increased competitiveness advantage because we will have fewer defects, our development and lead time will be reduced, we will have better market adaptability through portable solutions, and our code is going to be able to be done by anybody, anywhere, at any moment, in a sustainable pace. That means at the end of the road, improving our talent acquisition and retention. And we won't have any more excuses to develop complete embedded portable solutions made of reusable modules while using a common and shared language between business and between development and business. That is, that we will be finally able to express ourselves in the terms of the domain. Well, if you remember, we let the solution or the code in that stage. Now we are going to make it right, so we will move towards reusable drivers. What we need is to put in place an abstraction layer called processor abstraction layer. The PAL is aimed to hide the low-level details that each specific microcontroller unit internally performs in order to execute one of its possible tasks. For example, one of the modules conforming the PAL will be in charge of reading an analog channel, as we will see just in a moment. For sure, we will have an implementation of the PAL for each microcontroller that we want to use in our solution. This thin implementation layer is the only part of the code allowed to know and interact with the special function registers or anything that is related with the hardware. That is because it's the microcontroller or the hardware gateway. That means that it's fairly coupled to the specific microcontroller, but its duty. And also to the cross-compiler, no problems. It's exactly what we were expecting from it. This is why we call this thin layer the microcontroller firmware layer. In order to develop reusable IC drivers, we could use testdouble, which will implement the PAL at our convenience. We do not need to run the code until the hardware gateway for that. Of course, once the specs are established, we will exercise the drivers through the public APIs. The reusable IC driver test suite goals is to capture our integrated circuit datasheet interpretation, allowing us to implement it accordingly to the datasheet with introducing errors while removing the hardware bottleneck related to uncertainties and delays. Here we can see a test example of a multi-instance HVAC driver in C, a kind of temperature actuator using Unity and CMOC. It can be seen how the GPIO PAL SPICE are set up in the arrange phase, how the values of the GPIOs are put to unknown, and how the HVAC SAT under test is initialized. After calling the driver API in that line, to put it in normal heating mode, the expected values of the 5 pins controlling the HVAC, the output, it's asserted. After some refactorings, the same test looks like this. As you can see, the details are hidden behind proper method names. This is the kind of self-checking, always up-to-date documentation we want to end generating. And what about doing TDD in firmware, right? When we are working on a specific microcontroller unit PAL implementation, we cannot use any test double. What we need here is to assure that we are interacting with the special function registers correctly, which means that we need to assure that the sequence of reading and writing steps are done in the proper order and with the proper values. In order to do this, we could make use of the decorator pattern if we were in C++, for example, but if we are in C, the only thing that we can do is to have step spite hooks in the code, production code itself, that will be only compiled only during testing. This is a production code example in C belonging to the PAL module in charge of reading analog variables. If I manage to properly communicate its intent, you could easily understand what it does. It's a statically linked template pattern which executes every of the steps needed to get an analog measurement from an analog channel, delegating to each microcontroller implementation to define its concrete step, specific step. The goals of the microcontroller test suite goals is to capture our microcontroller datasheet interpretation, which will allow us to implement it without introducing errors, while removing the hardware bottlenecks related to uncertainties and delays. But what about the application? We let it violating dependency inversion principle and open closed because it was calling directly concrete IC drivers APIs. For sure, what we need is to create the proper abstractions related with those entities that only make sense from the point of view of the system application. Which I call system components. Each hardware variant will implement these abstractions in order to be used by the application. And for example, imagine that one of the system components is a temp sensor. If we have a hardware variant or PCB assembly which uses the STH11 IC as temp sensor, we will have a system component that will implement that by using the STH11 IC driver. That means that this layer is tightly coupled to the PCB assembly or hardware variant, but it is its purpose. How do we make our application independent of the components and the concrete hardware? Another pattern to the rescue, factory. We will use a factory that will read from a configuration file which components are used in the present variant or assembly, and it will create them. So so far we have been talking a lot about the hardware, but let's go for business development, right? What we want is to end using a kind of system arrangements, which will enable us to properly set up the scenario for each of the behaviors to be tested independently of the components used by each hardware variant. Each hardware variant will implement these system arranges abstractions accordingly to the components being used, and creating and setting up the appropriate PAL test doubles. In the arrange phase, we will also need to the main somehow instrumented in order to the test to be able to stop it and preventing it from running forever. We don't want that. Similar concept shown for the system arranges applies to the system assertions. These abstractions possesses all the methods to check that the system is in an specified status. Each hardware variant will implement these system assertions accordingly to the components being used, while properly interacting with the test doubles that were set up in the arrange phase. Once done, the application test suite will execute the main directly, and we will be capturing and accepting what is happening at the very low end of the system, just at the hardware gateway, with units of functionality independently of the structure or architecture that we have, one behavior after another in a slicing mode. The application test suite goals is to capture a product specification, which allow us to implement them without introducing errors, safely and incrementally from different products variants, yeah, right? Removing the hardware bottleneck, uncertainties and delays. One important thing that I want to emphasize here that here everything, all kinds of tests are possible, not only functional. We can do whatever we want here. Here you can see an application test example belonging to the temperature control system that we were talking about. Specifically, is assuring that when the system is in the ambient, the system is facing an ambient temperature that is inside the established margins, all the actuators must be in idle or reset state. It has clearly differentiated the arrange, act, and assert steps. I want to emphasize that this part. Oh, sorry. Sorry. This one, it belongs to the system arranges API. It's hidden all the details, but the arrange phase, the assert phase has not the same level of abstraction. As you can see, it's exposing low-level details related with the hardware or product variant we were developing in the moment we wrote that test. What we need is that violates open and close, open close and dependency inversion principles. What we need is a refactor here in order to create the system asserts API. Right, we need to move all methods to put it behind an abstraction. What we have accomplished with all of that is to have a plugin architecture. It means that we have drawn a line, and in which everything on its right side, which includes the hardware and the microcontroller itself, it's a plugin to the business logic. encapsulated in our currently decoupled and portable software application. Final bonuses, I'm just ending. Debugging is part of development. This is another fallacy and mantras. No, debugging is a shame. While debugging, we are adding zero value to our organization. Does that mean that I do not debug? No, I usually use the debugger. But the point is to be aware that when we are debugging, we have failed in all our previous steps. Measure your lead time in order to objectively know which are your bottlenecks. You will be surprised. Another of the fallacies that I hear is that TDD is a testing technique. No, TDD is a design and development technique, as I have said before. TDD, another of the fallacies is that TDD is for unit testing only. And related with that is that the unit under test is a class or a method. This is one of the most dangerous fallacies. No, the unit under test must always be an external observable behavior. If not, you will be coupling your test to a concrete or specific implementation that you won't be able to refactor. As a final takeaways, we can be agile if our code sucks. We can't improve our code if we fear to refactor it. And we can fearless refactor it without a comprehensive suite of automatic tests. As a final closing advice from the master Dijkstra, we should raise our quality standard as high as we can live with, because it's the only way of discovering how that boundary should be moved forward. And in my case, the only way I have found so far is by following TDD. This is the end of my talk. I hope it has been interesting for some of you. If there's someone interested in discussing anything, I will be over here and I will double check if there are questions. So thank you all. Gracias. Let's see. I don't know if we are in time. Let me check. Nope. I don't see anything. Okay, so I will be over here. I think that I haven't received any messages and any questions. I know that I have been running like hell because it was a lot of stuff, but I will be over here if someone is interested in asking me anything, right? Thank you for being there. Bye.